Whoa, spooky. Look at this. I got my hoodie. It's the middle of the day. I really shouldn't be doing my spooky ball, but I found out how I can just turn it on and off. And so this is the hoodie I got from O'Reilly. Pretty cool, huh? Check it out. I used to work with O'Reilly. So I want to continue where I left off with the dog here. I've spruced it up a little bit since the end of the last video, which was about creating a dog class. So this is a real dog, 2 colors of eye. We didn't get into eye color when I created my dog class. If you want to remember, this is the last video, so if you want to go back and watch it, I start out with a Python dictionary, and then I show how under the hood, a simple type or class with no more than a few attributes, such as color, name, and breed, is essentially a framework for storing a dictionary. You're basically, when you create an instance of the dog type, you're creating a specific dog as opposed to the generic dog, which basically wraps or sits on top of or contains dunderdict. What we mean by dunderdict is this dictionary, which is itself an attribute, right? And it contains all the other information we know about the dog. So then I had the dog bark, and I was talking about how an instance has a self. Like, if you want to think of a soul, that helps because it's part of the English language and many other languages that we glue the self, we glue attributes together with this thing called a self, right? So polyhedrons, now these are pretty much disintegrating. I still have that rhombic dodecahedron that's in the picture, and I still have the cube, but some of these may have, at long last, faded away. But it doesn't matter. I'm hoping that we can convince the educational supply people to make these in the right sizes so that we can have tetrahedron of 1, octahedron of 4, cube of 3, and rhombic dodecahedron of 6. It's easy to do. And I'm going to create a class polyhedron now, kind of like we did with the dog. And I'm going to give it just a single method, not a birth method, because I'm going to have the subclasses take care of that. But I'm going to have a scale method. And this is going to multiply all the edges by a certain length. So we would say, like, if I want all the edges to be double in size, I could pass in a 2. And what would happen to the volume? The self.volume would change as a third power of that. So self times self volume, whatever it is now, times n to the third power. And the self.surface area, we'll just call it area, it's obvious we mean surface area, I think, is going to be whatever it was times n to the second power. And I think this is important for, if I'm in a high school math class, the fact that any shape at all, if you don't change the shape, you just change all the linear, you grow it and you shrink it, but you don't let any of the angles change, meaning surface angles and central angles. If you hold all that fixed, then you're only changing the scale and not the shape in any way. Then you're going to get these precise changes in volume and area. The scale factor, I think it would make more sense to call this the scale factor. Let's just change that from n to the scale factor, which would be a linear scale factor, like I'm changing all the edges to be 1/2 of what they were, so I might use 0.5. Now, let's do the tetrahedron, and we'll just go ahead and get these others ready. Octahedron and cube. These aren't necessarily in volume order. And rhombic, because there is a pentagonal dodecahedron, which everyone thinks of first, because it's one of the platonics. And I'll just go ahead and say RH dodecahedron for that class. And here is where when we give birth, I'll just go ahead and assign canonical volumes. Like the rhombic dodecahedron, by default, is just going to be 6 because that's like the home base. Now we can always change that. We can override that, but for now we're going to go like this and create a rhombic dodecahedron of 6. And so then a cube, we can do the same thing. We can just make it be, what, 3, right? And if you know your American literature, this is all the Bucky Fuller paradigm, where we use the unit volume is going to be our tetrahedron, right? So that's kind of odd. Some might say it's topologically simple. It makes sense that we would explore as an alternative a different shape as our unit. I mean, it's surprising to me that we had to wait until Bucky Fuller to get going on this particular research. But now we're well along, come a long way. So there's the beginning, except what? I haven't actually told any of my polyhedron subclasses that they need to inherit from polyhedron. And what's this going to get for me? This means that they're all going to inherit the scale method. And you know what? I haven't started out with an initial surface area for any of these things. And I think in the interest of time, in order to keep this video short, I'm just not going to worry about area. I'm just going to stick with volume. So there we have some object-oriented programming where we have 1, 2, 3, 4 subclasses, all polyhedrons, inheriting from a generic polyhedron. Now we could have a rotate method up here. We might do various things to flesh this out more, but let's just check this one so far. So let's create a tetrahedron and ask what its volume is. And because it just takes the generic canonical concentric hierarchy volume as its starting point, that's what we do. Now, let's scale the tetrahedron, T scale, and let's make all the edges be half of what they were. So the scale factor is 0.5. I could just pass in the fraction 1/2, same difference. And now we'll ask what the volume is. And it's gone down to 1/8, right? And let's say octahedron. We'll just get an octahedron that simply, and its volume is going to automatically be what? Canonical volume 4. And you get the idea. Now the tetrahedron and the octahedron together, these fill space and create the octet truss. So what you might want to do at this point is turn the next cell into a markdown cell and go find an octet truss. Like I would just go to my Flickr photo stream and type octet truss, and I don't label all my slides by a long shot. So the selection that I have here is going to be rather small compared to the total number of choices that I'd have if I were to label everything. But even so, this is the Portland World Trade Center that came up, and that's perfectly acceptable. So I'm going to go octet truss is tetrahedrons and octahedrons. I could explain that more, and there we have it. There's an escalator going up. This is the size at which octet trusses tend to be built in this day and age, right? Pretty big. Fuller did have a patent on that for a period. Okay, so that's what object-oriented programming looks like. We started out with the dog. We created instances of the dog type without any inheritance, except inheritance is implicit in the fact that all objects are inherently classes of, or all types, I should say, are inherently subclasses of object. But because that's always true, we never have to say it's true at this point. We don't have to explicitly do this subclass of object, but we could if we wanted. Now something I might suggest, let me run all of this kernel stuff, restart and run all, is if you're teaching this in the military, like if you're at West Point or you're teaching this in some military academy, you want people to understand inheritance. what we call the message resolution order. So like when I go and invoke the scale method on my tetrahedron, clearly the tetrahedron itself doesn't have a scale method. It only has a birth method or dunder in it. So where is the scale method? Well, it knows to, if it can't find it in itself to scale, it knows to look at its parent classes. In other words, to pass the buck up the chain of command. So instead of method resolution order, if you want to teach a more military vocabulary that's already familiar, you could talk about the chain of command. So like the polyhedron is the more general. The polyhedron in general knows the scale method. And then the individual specialists, they each know just their own canonical volume to start with, and they all share the same scale method. So when I ask the tetrahedron to scale, it goes, wait, I don't know how to scale. Pass the buck up to the polyhedron level, and there, even so, the self is going to refer to this particular tetrahedron. The self travels up the tree until it finds a name that it can resolve with, i.e. scale in this case, does the deed, and it's the volume of that particular tetrahedron that then gets modified by the scale factor. Okay, hope that was interesting. That's how easy it is to make a Jupyter notebook. At this time, we could just save it as, we could rename it, for example, give it a name, OSCON 2019 OOP for object-oriented programming, rename, save it again, and now I could put it out on the web, right? And you guys could grab it, that kind of thing. That's simple. Recommended for high school. School of tomorrow, school of today. All right, talk to you soon.